When an electric current passes through a resistor, the resistor heats up. This heating effect is called Joule heating, and we see this quite often in our homes. Whenever we turn on an incandescent light bulb, so for example a light bulb with a tungsten filament in it, or an electric heater, or a toaster, and so on. Joule heating is the process where electric energy is converted into heat energy when a current passes through a conductor with some resistance. Now, in the last few lessons, we learned two different equations. One was showing us how to calculate the power produced or dissipated from a device in a circuit, for example, a heating element, and this is equal to the voltage drop across both ends of the device multiplied by the current flowing through it. And the second equation was about how resistance of a device in a circuit is related to the voltage drop across it and the current flow through it. We found that the resistance is equal to the voltage divided by the current. But we can also use these two equations to represent the power produced in terms of the resistance of the resistor, and this power will help us calculate the Joule heating in a minute. So I've drawn a quick diagram here with a simple battery or power supply connected to a heating element, and this heating element is effectively our resistor in the circuit. If we rearrange the resistance equation to make the current the subject of the formula, we find that the current is equal to the voltage divided by the resistance of the element. So we can use the current here and insert this equation into our power equation. So the power is equal to the voltage multiplied by the current. In this case, the current is equal to the voltage divided by the resistance. So we end up with the power is equal to the voltage squared divided by the resistance. We can also rearrange our resistance equation in a different way by making the voltage the subject of the equation. So this time, the voltage is equal to the current multiplied by the resistance. And again, we can plug in this term into our power equation above. So the power now is equal to the current multiplied by the resistance multiplied by the current. In other words, the current squared multiplied by the resistance. So going back to our diagram now of our heating element, if we know the heating element's resistance, then if we just measure the current or the potential difference across the device, we can work out its power output in watts, which also has units of joules per second. So let's do a quick question. An electric kettle has a power of 2.2 kilowatts at a voltage of 240 volts. Calculate the resistance of the kettle element. In other words, the heating element within the kettle. So given our two new equations that we've just derived, which one of these could we use to find the resistance of this heating element? So if we use this equation here, where the power is equal to the voltage squared divided by the resistance, we can rearrange this equation now to make the resistance the subject of the formula, where the resistance is equal to the voltage squared divided by the power. Plugging in these values and making sure that we square the voltage of 240 volts, we get a resistance of 26 ohms, and we've rounded this down to two significant figures. And we're going to use this value in another question at the end of this video. So now we can work out the power dissipated by a resistor or heating element, but how can we work out how much heat is emitted over a certain time period? So to do this, we can use Joule's law. And Joule's law is written like this, where the heat emitted by a resistor is equal to the current squared multiplied by the resistance multiplied by the total time that electrical current is moving through the resistor. And if you notice here, this term, I squared multiplied by R, is simply the power. So we know that the heat emitted from any heating element in a circuit is equal to the amount of power dissipated from this element multiplied by time. And the units of heat are joules. So this formula shows us two main things. If we double the current moving through our resistor or heating element, we quadruple the amount of heat it produces per unit time. And we'll also see that if we increase the element's resistance, so the resistance to the flow of charged particles or currents through the circuit, we increase the amount of heat output by a linear amount. So if you double the resistance, you double the amount of heat produced per unit time. So now we can use Joule's law in combination with the heat capacity equation. Now I covered the heat capacity equation in a previous video, and I'll put a link at the top here so you can have a look at it. But basically, the heat capacity equation tells us how much a substance will heat up, what its change in temperature will be, if we supply a certain quantity of heat to the substance, where we know the substance's mass and we know its heat capacity at constant pressure. So for example, if you got a kilogram of water, we know that the water has a heat capacity of 4,200 joules per kilogram per Kelvin. And if we want to heat up the water from 0 degrees Celsius at freezing point to its boiling point at 100 degrees Celsius, we can work out how much heat we need to supply to this mass of water. So let's try a question. If we have 1 kilogram of water in a kettle, and that water has an initial temperature of 20 degrees Celsius, and we want to increase it to 100 degrees Celsius or boiling point for water, if we know the current and resistance of the kettle's heating element, can we work out how long it will take for the kettle to heat up a kilogram of water from 20 degrees Celsius to 100 degrees? So if we use our previous question earlier in the video, we found that the power for our kettle was 2.2 kilowatts when there was a voltage of 240 volts. We worked out the resistance of the heating element to be 26 ohms. Now it's also important to find out the current going through this circuit. And previously in this video, we learnt that the power is equal to the current multiplied by the voltage. And we can simply rearrange this to make the current the subject of the formula. So the current is equal to the power dissipated from the heating element in the kettle divided by the voltage drop across the element. So we got 2.2 kilowatts divided by 240 volts, and we get 9.2 amps to two significant figures. Now for the remainder of this question, I'm going to assume that the resistance is exactly 26 ohms and the current exactly 9.2 amps. This simply makes our calculation easier as we go through this process. We also got the mass of water, which is at 1.0 kilograms. The heat capacity of water at constant pressure is 4,200 joules per kilogram per Kelvin. And the change in temperature is 80 degrees Celsius, or 80 Kelvin, which is simply 100 degrees minus 20 degrees. So Joule's law shows us how much heat is emitted from a heating element, and our heat capacity equation can tell us how much heat is required to heat up a body of water in this case. So on the left side of the equation, we've got Joule's law, and on the right-hand side, we've got the heat capacity. And we can rearrange this equation now to isolate the time. And this will be the time it takes to heat up the water from 20 degrees Celsius to 100 degrees Celsius. Now we plug in all these values here, and to two significant figures, we get a value of 150 seconds.